Yeah, I would like to talk about one of my top three most favorite topics in Prometheus land, which is histograms, past, present, and future. First of all, this is not a how-to. There are gazillions of talks and blog posts and how-tos and everything on the internet about how to use Prometheus histograms. There's a lot to say about it. If you haven't used them or you use them in the wrong way, there's a link. Does that work? No. So there's the link to the very old but still very valid best practice document on our web page, and you can just take it from there, I guess. So the idea of this talk was to first start with the past of histograms, not so much to explain you how they work, but more like why they work the way they do. And I kind of was tempted to have a subtitle like Secret History of Prometheus Histograms. Unfortunately, that was all when I thought this talk will be 40 minutes. So we have to skip the past because we have only 20 minutes. There will be, I hope, at some point I can give the director's cut of this talk and then I can put all the secret history in it. So we have to jump to the present. Mostly looking at what really works well with our histograms and what doesn't work that well. And then, of course, later we will look at the future, what we might improve. Okay, part one of the present, what works really well. I summarized it all on one slide. So these questions that I have put here, these are questions you might have asked. What percentage of requests in the last hour got a response in 100 milliseconds or less? I think this is one of the most relevant questions in observability or whatever they call it these days. Also like stuff like between certain time frames. This is what Prometheus histograms can do perfectly, almost perfectly accurate. Updex, if you have never heard about it, you can look it up. It was mentioned in one of the talks. That's very similar to this same thing. So these are kind of the relevant questions. There are two things that are perhaps not that well known. The one thing is really important. You take it for granted, I guess, as happy Prometheus users. We can mathematically correct aggregate histograms, or sometimes it's called they are mergeable. And this is what many people still get wrong. Like the shortest version is you cannot aggregate pre-calculated quantiles. There are still talks and flame wars on the internet about it. It's really quite amusing. The other thing, and this is what you might probably have missed, high frequency sampling is feasible. Like you could totally tell your Prometheus server to scrape your target every second. It would every second sample the histogram and you have 1 second resolution. Or 500 milliseconds even would probably still work. Like there's the incremental cost of making the sampling more frequent is really low. And that's also something that many other setups, competitors, whatever, don't do. So keep that in mind. We'll play a role later. So this is all what works well. There are asterisks almost everywhere except the high frequency sampling, which makes it even more awesome. So all the asterisks are essentially one thing, if suitable buckets defined. So here you need a 100 millisecond bucket, here you need a 4 kilobyte bucket. For updates you need your tolerated and target value, whatever they call it. And even for the correct aggregation you need compatible bucket layouts. I'm not saying the same because you can have compatible layouts if you just subdivide buckets. There we did some trickery with cumulative, difficult word, cumulative buckets. But everything requires that you have predefined the bucket layout in the right way. So this is already one of the problems. We will come to that later. So now a list of problems. I left out all the very subtle problems that might still bite you badly, but they are too subtle to explain in 20 minutes. So incomplete list. So this is not the problem. This is actually why we created histograms back then in 2015. The idea was we want to calculate 99th percentile latency, median latency, and we created together with histogram this infamous function, histogram quantile. So what's wrong about this? Kind of nothing is wrong about it, but there are problems. Interestingly, nowadays, I think the question I had on the previous slide that work really well, they are, in my opinion, way more relevant in modern observability land because this 99th quantile is totally overrated. But still, sometimes you want to know it. So what's the problem? First thing, the accuracy depends on your bucket layout. If your 99th percentile latency is quite close to a bucket boundary, great, it's very accurate. If it's far away from a bucket boundary, not so great. So obviously, countermeasure, just have a lot of buckets. Problem, buckets are expensive. So what we recommend, kind of more or less officially, just put your bucket layouts where you think you have interesting values. If your SLO latency is something like 100 milliseconds, put a bucket boundary there, and it's great, right? Okay, let's keep it there. The other thing is the asterisk, essentially, but now for this thing, bucketing scheme must be compatible across aggregated metrics. So these might be many metrics. Histograms do correct aggregation if the bucket layout is compatible. But also across the rate calculation, which is 5 minutes here, that's kind of easy to keep the same bucket layout over 5 minutes. But this could be days in certain use cases where you have to pay attention that you haven't changed your bucket layout in incompatible fashion in that time frame. Now, why would you ever change it? The bucket layout, you come up with one and you'll be done with it. Now, I just said in the previous point, we tell people put the bucket layout, put the bucket boundaries where you have interesting latency values. So if you got the next generation CPU or something, or you optimized your code and suddenly you have half the latency, then the interesting values have just changed and you change your bucket layout. So kind of this is all related and it makes each other worse and it has all to do with buckets are too expensive. This is where I have to be like this judicious bucket layout and have to change it all the time. Meh. Okay. The other thing is really completely independent. That's the ingestion isolation. Ganesh already talked about it. If you ingest a scrape in Prometheus, the scraped samples will show up one after another in the TSDB, which is like fraction of a second. It's not bad usually. But if you hit different buckets, like if some of the buckets are already updated in the same scrape and others are not, this could, under circumstances, create really weird results. And if you aggregate a lot of histograms from different targets, the likelihood that you hit that case is increasingly high. And we want to aggregate. This is why we created histograms, to be aggregatable. So this is kind of bad as well. Okay, final thing. This is almost precisely the slice. I have done too much go. This slide that Chris used. This is how we recommend you should do the partitioning. You take a counter for your HTTP request and you partition by status and method and whatnot. And then you have a histogram that you are not partitioning. Why? Because buckets are expensive, right? So this is just a multiplier in your cardinality. So now I have found, Chris just said it's great, right? You just do this, and if you really need precise information, you go to your event processing system. But I'm always, I'm always recently I got increasingly annoyed by that because I had a lot of those. Okay, I get a 404 storm. How fast am I actually responding to 404s? Is that okay, or is that creating my outage right now? Or I get like 503. Is this like, do I have two different timeouts I hit, like two different populations, or is it all the same? And of course, I still want to know like just my 200s, how fast they are while I have a 404 storm or something. I find myself quite often in that situation. Again, you can partition your histograms, but that you have to be super stingy with your buckets. Okay, the future. How we timers? It's okay. The future is kind of difficult to predict, but I pruned the problem list in kind of some manipulative way, but we have only two problems, essentially. The one is buckets are too freaking expensive, and the other is isolation. So look at different options. Option 0, I call it 0 because it's not really an option. We're doing it anyway, fixed isolation. So Ganesh explained that already, so I don't have to do a lot about it. But I should mention, this was already treated here at PromCon 2 years ago. It was my most favorite PromCon talk. It's probably the one talk that everybody forgot who was there 2 years ago because you were just open-mouthed and had no idea what this guy was talking about. This was Brian's staleness talk, right? But it was also about isolation in the end. And I loved it, but interestingly, I looked up the slides. It was written like, I'm almost done with that. And that's the pull request number 105 in TSDB, which then got redone by Gautam in 2018. Ganesh already explained that, right? So we have to pick this up. We have to get it done. It might have a slight performance penalty, but like ingestion is just very fast anyway. So we will do this, and isolation is done. One problem gone, which leaves us, yeah, okay. I thought it was like silently weeping now. Buckets are too expensive. So what can we do? Option one, we do nothing. So, I mean, we lived for that like forever. Like 2015, we created histograms. This was not a surprise. We were totally aware that this is a problem. And we said, yeah, I mean, we will live with that. Now, there are various reasons why I don't think we should do nothing. The one is Prometheus is kind of popular by now, so we get backlash. I see a lot of like people complaining, spreading thought and everything. We could all say, well, we don't care. Like, if they don't want to use our awesome open source monitoring system, it's their loss, right? But it's kind of, there is usually a root, like a true thing in this, and often it has to do with histograms, or just that they are difficult to work with, or you have to predefine your bucket layout, or whatever. So I think this is also essentially what Chris said, like, confirms what I was thinking. You just switch over to your event processing system if you have to answer like difficult questions. Fair, right? But why not do this within Prometheus? Okay, whatever. But there's also a reason where I think as an engineer or as like somebody who was in the project for a while, I think this should be improved. And that's one of my proverbs. My other top 3 favorite topic is Prometheus proverbs. Instrument first, ask questions later. That's one of the proverbs. That essentially means you can just do a very low-level instrumentation in your code. You don't have to think a lot, and then later you can ask questions. For histograms, that doesn't really hold, because you have to know your SLO, what latency values are interested. You cannot partition, so you cannot later ask for 404 specifically, all those things, right? So I think we are not delivering that promise, and I really would like to improve this. I have liked that for quite some time. Okay, so option 2, make buckets a bit cheaper. We can just make it a bit more efficient, right? There should be some ways of doing this. And I see 2, like this is kind of the low-hanging fruit thing. And I see 2 like attack vectors. The one is the exposition format and the other one is the TSV. So this is the exposition format as you have it now. You see like the bucket boundaries look really wild. That's because it's taken from the little example program in client Golang, and this doesn't just hardcode the boundaries, it calculates them. And then you get those like floating point inaccuracies. So this is not frequent. Like often you just hardcode and you say my SLO latency is 100 milliseconds, so I hardcode it to 0.1, and then it looks not as bad. But it's still like if you calculate the bucket boundaries, and this is often a very reasonable approach, it's just more sophisticated, so not so many people are doing it, you get those weird things. And then you see it's really repetitive because this metric name is repeated all the time. And I didn't even partition this histogram following our best practices, but perhaps I want to, right? And then it gets even more blown up. So this is 1,676 bytes for a single non-partition histogram. Our usual excuse was that compression saves the day. Prometheus uses compression by default, and indeed, if we gzip this whole thing 330 bytes, that's fine. But I think this is a bit of a, kind of a dead alley or something. There's this cube state metric story where Max Inden found out the compression is actually more expensive than the network bandwidth usually. So for cube state metric, which just dumps hundreds and hundreds of megabytes of metrics onto the wire, they by default disabled gzip compression because it was just faster. Faster even, like it's mind-blowing. So even if compression would be free, if you have a lot of this, somebody has to render this, and somebody has to parse it. Like the parser is super optimized, of course, but still, it's a cost, right? Now, interestingly, we had a less repetitive exposition format, protobuf. I mean, labels are still kind of repetitive, but it didn't need to repeat all the metrics, and it has all the floats as just floats, like binary encoded. If you do the very same thing, it's 357 bytes in protobuf. If you compress that, weirdly, it's not compressed much, and it's even larger than the compressed text format. Okay, so, but the kind of the interesting thing is it doesn't even need compression. So we could have gone down that way, but now we have just learned open metrics is almost done, so we are kind of stuck with the left side. I would also say that there's still a lot of numbers in there. So there was a short discussion when Prometheus 2 dropped the protobuf format that we should make this more compact. And one of the suggestions looked like that you just have the metric name once, and then you have all the buckets with their count, and then you have the sum and the total count in the end. I don't know why this never got traction, but this is already much better. It's like 7, it's not on this slide, it's probably in my notes. It's 702 bytes. So it's like twice as large as the protobuf, and a more like hard-coded bucket layout would be quite nice. But it's still a lot of numbers, and numbers in text is kind of not very efficient. So if you want to be super efficient, we would like some binary format. We could also do stuff like whatever, some kind of compressed warbit encoding of the counts, and we could, if we have a partition histogram, we could have the bucket scheme only once and not every time repeated. So there is some potential of optimizing this, but it would be a different exposition format. Okay, let's quickly look at the TSV. This is how you can query a histogram in the TSV. Interestingly, this looks really similar to the text format. And that's not by coincidence. That's because the text format was informed by the way that Prometheus saves time series in its TSV. And the problem is that the TSV has zero notion of histograms. What we just do, we save every bucket as a time series, we save the count and the sum as a time series, and since we cannot have like floating point values as label value, we encode the bucket boundary as a string. And then when we read it again and we have to like do math on it in the histogram quantile function, we pass it again as a float, which is a bit weird anyway. This is not as wasteful as it looks because there are symbol tables in TSV and all those things. So I think the biggest potential of saving here is that every bucket is a whole series in the index. I'm not even so sure it would help so much, but it would help perhaps a bit if we could just teach TSV to treat a whole histogram as one value, similar to a floating point value. And then we have just one entry in the index per histogram. We could also leverage this then by doing some compression. We have the double delta for sample values anyway and timestamp, but we could perhaps something cross buckets, like buckets always go up and they have certain patterns that might compress nicely. So this is also something we could think about. And then we could still make it all compatible that for PromQL, for the evaluation engine, it would still look like this. So this could probably be done as a non-breaking change. But yeah, would help a bit. Okay, but I think to make it really nice, we have to make buckets a lot cheaper. How about having an infinite number of buckets? And like every bucket boundary is just 5% above the previous one. So we have like a 5% error margin on everything. That would solve our bucket change problems because that bucket scheme would be so rich we never need to change it. And it would also be super accurate. Whatever value we have, we would deliver our promise. We just have to make it cheap. Infinite number of buckets, infinitely cheap or something, sounds like not a great option. However, there are those more or less famous approaches that kind of follow that, that idea. HDR histogram is super famous. Surconos has for their proprietary metrics offer, or whatever it's called, hosted metrics, they have this LL-hist, log linear histogram, which the library is open source, like they have open source everything about what they're doing there. And then there is very hot paper, science porn, DD sketch from Datadog. It looks like mathematically super sophisticated, but it's actually very similar to this Surconos thing. It's actually very simple. It's essentially infinite number of buckets with a more or less fixed schema. And the only secret for all of them is it can handle sparseness. So empty buckets have no cost. And that's what we are totally not doing in Prometheus. So if we wanted to adopt something like that, we have to change everything to handle sparseness. So that would be very invasive. But it would buy us quite a bit here. There's another thing. Okay, we're running out of time here. Another thing is how they aggregate stuff. So this is a single histogram. Then you have histograms from different instances. They should all look slightly different. I was just not had no time to make them different. And then over time, this is what they do. In general, all those metrics providers, they always collect a histogram for 1 minute and then send it over to the metrics provider. And then they reset it. This is why sparseness works really well, that because every minute they start from an empty slate and then every bucket is empty and has no cost, and then they slowly fill up. In Prometheus land, we do something different. We accumulate the histogram forever, and we take deltas between 2 points in time to calculate our percentile and whatnot in this time frame, which is good because it gives us this resolution that could be once per second or something. They have just a 1 minute resolution, which like Ben Siegelman doesn't like that, for example. So we have a good approach, but this accumulating forever is a problem with sparseness. I think there are ways out of it, or to at least mitigate it, but we don't have time for that. So let me quickly go to option 4, some kind of digest or sketch. DD, Datadog, call their stuff sketch, but I think it's not really a sketch. This is something, so philosophical, we had this also at this conference, like if this and this is problematic, you should perhaps not have it. If buckets are expensive, perhaps you should not have buckets. So this is all about finding a solution where you mathematically represent kind of the shape of the histogram in some weird way, in some digest. This is the same problem as before. All those algorithms, there's like huge pile of papers from the last, 20 years. The early algorithms had this problem. They were not mergeable or aggregatable. Now the more modern, they have this property. They are mergeable. You can do this. But then again, for Prometheus, we need this subtractability. We have to take deltas. And the best candidate, more science porn, is this thing here. I think I put it here. Yeah. This is the same thing in big. So this is the moment-based quantile sketch thing. And this almost delivers the promise of being like subtractable. It's hilariously complicated. That's the like 10-page appendix just with all the maximum entropy proof and whatever. It's fascinating. It's really fascinating, and I'm really sad. I think it doesn't work for Prometheus, even if we were willing to change everything. I'm still in discussion with my boss, Tom, and with another guy, and I have to make sure of that. But yeah, I think the delta thing doesn't really work completely. And also, I think the biggest problem with all those sketches is long tail latency, which is the one we are interested in. It has it's an estimate, and it has an error margin that is just too big, in my opinion. Or even in Datadog's opinion. This is why they wrote the other paper, and they probably called it sketch, so it would resonate, but it's not a sketch. And especially this question, like how many requests have reserved below 100 milliseconds? Like what percentage? I can answer this precisely, and this is wishy-washy with that. So, okay, quickly my hit list, the 4 options. I mean, we do isolation anyway. Do nothing, I already said that, I don't like that. Digest sketches, fascinating, super nice science, mathematics, but I think it doesn't help us, and it kind of weakens where we are strongest. Make buckets a bit cheaper. If we can do nothing else, I want to do this, but I would really like to do this like in the close future to work on this sparseness problem, and if we can master that, we can do something like that. Okay, thank you.
Oh, thank you, Björn. So, questions?
Are you confused now? Do you want to repeat that?
I can't guarantee he's just going to not just going to hand you a paper.
Perhaps I confused them more than your
Well, I asked earlier.
stock.
People remembered it, but it turns out we actually don't have that many people who were here 2 years ago, which I guess is a good thing.
Brian, the other Brian.
Hello. I'm sort of asking as someone who codes on bits of this and alternative implementations and so on, is other than the histogram functions with the sum rate and so on that I have to copy and paste because I have no idea how to actually write that line. Yeah. Are there other uses, I mean, beyond just kind of inspecting the data and so on? Because I kind of felt that a very specialized data structure for a histogram made sense to me. But I don't know enough about how that data is used. So, like, are there other ways in which the data is used other than feeding to that function?
I mean, the initial questions that work really well, they just work directly on this bucket time series, because the 100 millisecond time series, which you call LE equals O.1, hopefully. That's the time series I want to look at to calculate that, and you kind of dig directly into this, which is fine. And it even makes sense to have this as a separate time series in that case. And histogram quantile looks at all of them at once, essentially. But yeah, that's the only case where we kind of retroactively reconstruct this complex data structure virtually, if that makes sense. Tom nods, but he's my boss. Yes.
This is
You want to give a statement?
Am I allowed to? This is how we, like the SLO-based error budget alerting that's very popular right now. That's how we do it. We look at just one of the buckets, like the SLO bucket, basically.
And for updates, you have to look at two buckets because they have two latency values, and then you have to predefine them properly. Well, like the Serkonos approach, essentially, they have 110 milliseconds, 120 milliseconds, 130 milliseconds, and so on. And this is what, like, what's the Serkonos guy? I forgot his name.
Theo?
No, the other one, the statistician.
I've forgotten.
Anyway, he told me this is what, like, product manager just want. They never would tell you 123 milliseconds SLO. They always say 110 or 120, and then they have the suitable bucket already in the histogram. That's kind of the idea. Okay, there was another question.
Wait. Because we have people listening to this afterwards and online right now.
With this sparse representation, does that have any implications on the exposition format for the client libraries?
So I think if we want any super empowered histogram, we need a specific exposition format for it. This is the kind of the sad part. Tom was kind of speculating, can he just shoehorn it into this normal thing? I think it will have a lot of numbers. Like the Serkonos histogram has essentially 40,000 buckets. But they are not a lot of them are used, but we cannot do the cumulative thing to be sparse. And I think we have so much numbers in there in the end that we need some kind of binary encoding. I mean, this is all speculation now, right? This is the beginning of a research, and I wanted to give you this, like, now that I have more time to work on that, if my boss wants me to do, but responsibility. Now this would
The question is, does it conflict with open metrics?
Yes, I mean, this would be outside of open metrics, or it would be open metrics 1.1 or something. Okay. I don't know, like this is totally, yeah, kind of beyond that. There was one more.
Slightly related subject. So, in the future, do you think that we can ditch summaries? And this question also to you: in the open metric standard, would we have summaries?
Ah, yeah, good question.
That's an open metrics question. Yeah, we've got the summary still in open metrics for the same reasons. Summary was first in Prometheus, the histogram came later. But the thing is, just so many things out there that expose quantiles that to be compatible with them and keep them on board, precisely, it's still there. Like, it's discouraged, but it's still there.
Like the Go garbage collector exposes internal metrics about the 25th, 75th, and median quantile latency garbage collection duration, and we just mirror this directly into Prometheus with the Go client, and this is just a summary, right? And also, like Brian will always say, the sum and count alone is already quite valuable. So this as a summary is always nice, and sometimes you don't want to aggregate. Like, who wants to aggregate like garbage collection times across the whole fleet? Like, you want to pinpoint that this one process is kind of weird, and then, yeah, it makes sense to have that. Also, the Go runtime doesn't give us anything else.
Okay.
But there are cases where it makes sense.
So we're going to be starting lightning talks very soon. So,
okay. Somebody gets wired up.
yeah, I'll let Rob have his question. So if we could have Ulrike, Arala, and Jarvis Buchan.
I
Basement
think
skyscraper?
somebody wanted to ask something.
Yeah, I was just going to get
And
them
then
up. Parallelize a
free
bit.
up the
No, it was just Rob.
computer
That's the last
space.
question.
Björn, I just wanted to ask
Was mine?
what your thoughts are on
Sorry? Now I got distracted, sorry.
Sorry, I just wanted to ask what your thoughts are on T-digests, and which is another mergeable data structure.
This is not the hottest paper. It's on my pile of papers at home. I think, as far as my research went, this is a while ago, I think T-digest doesn't do this subtractability thing. And it's also same problem. I think it's even worse than the moments-based. They compare, like everybody claims that the others are worse, of course, but they have a lot of data to prove that. And I think the moment-based stuff here, this is really the hottest and sexiest, and I think they're a bit better per effort unit than T-digest. And they have this potential of being subtractable, although I have my doubts. So it's really, really complicated, and I think in the end we want precise 99.9th percentile latency, and I think they will never deliver that. This is unfortunately how it is, I think.
Right.
Okay.
Thank you very much, Bjorn.